Ladies and gentlemen, I would like to introduce a very special guest this evening. Directly from London, he's a specialist in parametric design in the industry of architecture. I would like to warmly welcome my good friend and a world expert in parametric design, Arthur Mamou-Mani. So Arthur, please take it away.
Thank you, Jan, and I'm happy to be here. I'm happy you made that space for me. My name is Arthur Mamou-Mani, and I'm an architect and a teacher as well, and located in London. This is sort of what I would call my ecosystem. Mamou-Mani is my practice. I teach at University of Westminster. I also teach a software called Rhino and Grasshopper to many practices through Simply Rhino, and I also have my own Fab Lab called FabPub, which runs in parallel to my practice. The work that I will show is a combination, a kind of result of all this ecosystem, which includes projects with 3D printing, of course, but I guess what I'd like to do is to expand the concept of 3D printing to a wider notion called digital fabrication. Digital fabrication is what enabled the process and the making of those projects, and allowed me to be more than just a designer remote from the creation, but actually the maker of those creations. So these are a couple examples. I'll go through them in more detail, from small to large, from built to unbuilt. So this is the kind of behind the scene notion that I work with, computation. So how the computer can be part of the process, how it can not just be the tool, but also the actual kind of collaborator. The computer becomes the collaborator in that it unites many concepts and creates what's called a generative model. Now, to do that, you need a lot of tools. This is Grasshopper, all its plugins. You know, if you know the ecosystem, that's most of them. It's missing some. Sorry. You know, from physics engine to environmental simulation, all the way to 3D printing, which I'll show later. Basically a lot of tools that allows to unite your model with different constraints. Now, our space is located in what's called the Maker Mile in London. We're very lucky. Somehow it happened that the studio ended up amongst many maker spaces. Maker spaces are the way that we can turn open source designs, such as the ones here on the Instructables, into physical objects. So turn the digital to physical objects. Of course, this is how you go from not knowing to knowing when you're self-teaching a lot of stuff. Forums, from the Grasshopper forum all the way to the Instructables. You start learning. That's how I learned. One of those annoying forum users that ask questions all the time. And this is our platform where we share back the knowledge with our students. So these are examples with Toby Burgess, my colleague, in which we shared our students' work. So I'll go through all of it in more detail, but this is general introduction. This is FabPub. So this is next to our studio, the shipping container that contains our Delta Tower and our large laser cutter. And people can book them online and use them so that they can, reproduce or expand on our designs or their own designs. And of course, it always takes really open-minded clients to do so. Now, something that I've wanted to implement in my practice is that instead of necessarily waiting for a client to come, as we do when we're the usual architect, is to actually generate your own project or generate the money that can actually finance us. So hence the numerous Kickstarter campaigns we constantly do. All right, so since this is about digital fabrication and 3D printing in particular, I'm going to take you through my journey with 3D printing. This is one of the very first projects I worked on with Guan Li for the VNA, and it was based on a cloud. So Guan approached me and said, can we design a cloud, and use 3D printing to manifest it? Now, clouds, they have rules behind them. We expect a certain shape, but this shape happens because dust particles are being covered with little particles of water and suddenly start scattering the light around. So these are examples of tests we did in the computer, and then later on 3D printed them in order to catch the light and do the same scattering effect that happens within clouds. We were, of course, constrained by the technology, in this case, a Z-Corp powder printer, which meant that we can only use a certain thickness, and we can only use a certain amount of material because of the cost of the powder. Now, this really informed this project. So I find it's really interesting when the tool is directly influencing the creations. And I find it really hard if I didn't have a tool, I wouldn't really know, what I could design. So it's a real collaboration with the machines, always. So here we go. We were lucky because we could print a lot of stuff and it was next to us. And that's how it happened at that time. This was maybe 5-6 years ago. And we would inflate these sort of cloudlets, we call them, which looks more like mushrooms than clouds. But they would capture the light, and because they were inflated, they would need very little material. Inflated in the computer, of course. So this was the assembly of it. The thing is that we realized the cost that it would take was incredibly high, and it was really hard to convince the client, which completely informed the next project here. This is as close as it gets to 3D printing without 3D printing, but using a similar effect. So I remember working with a collaborator at the time, Jack, and he was like, "Oh, I know a material that does the same thing as the cloud, but is a fraction of the cost." It's what you find in bags. It's called spacer fabric, and here was a case of simulating the behavior of that fabric inside the computer. So we defined the angles that the fabric would resist at, and then we pinch it and look at the patterns that it creates. This was for Karen Millen, which is a British designer, and the brief was to design a window display for them, a 30 meters long window display. So the problem is, the budget was very, very low. So what did we do? We used the same scattering effect as for the cloud prior, but we used it with fabric, and we shaped the fabric with cable ties. Now, as soon as you use low technology like this, what you can do is marry it with your algorithmic model, so with Grasshopper. So we would vary what's called a smoking pattern and vary the distance between these patterns in order to shape the fabric and give it more or less resistance. Now, this is the kind of geometries that would emerge from that process, which meant that we could actually tell a story. But the story came after having tested the material. So again, it wasn't necessarily the drawing that came first, but more testing of a material and seeing the potential of that material. So these are a couple views of the project. I think one of the journalists called it like a 300 meters long dress because we used 300 meters of material. So each mannequin had a relationship with the piece, and at the end what happened is Karen Millen used the material to do dresses, and we dyed the installation to the color of the dresses as well. So there was a direct relationship between the two. And then I discovered FDM printing. So what happened is throughout the process of understanding the costs of 3D printing, I quickly realized that it would be really, really hard to use it unless there is a way we could just make it faster, cheaper, and if we could have a better control over the files. Now, I have a good friend of mine and colleague from the Architectural Association called Adam Holloway, who came with a massive Grasshopper definition and said, "Arthur, I think we can generate G-code directly from Grasshopper." And, and I thought that was brilliant, because that could mean that instead of designing the shape, you design the toolpath. And so we decided to write a plugin together. I knew how to write plugins. He knew the whole thing about G-code, and then we collaborated and made an open source project called Project Silkworm. ProjectSilkworm.com. It's downloadable, and this is what it produced. So this is called G-code. You probably know it. Oops, sorry. And it's just an X, Y, and Z coordinate, and some information like E for extrusion, or G1 for extrude, or things that set temperatures and so on. So what happens is, by designing the path instead of designing the shape, you don't need an STL file. You just directly work with lines. You plug them in Silkworm, and it exports vectors, and the vectors into lines of G-code. So something was happening there. One of our students, Andrei Jipa, started researching more in detail what could be the equation behind the generation of the G-code, and here did a diagram explaining the cross-section of how you would calculate the volume of extrusion per line. And based on that, we collaborated on an actual full-scale 3D printed pavilion, which led to this kind of weird modules, which we thought we could use as a kind of three-dimensional brick that we would connect without the need for any glue. That was in spirit, using this male-female connection. Now, based on speed and based on the constraint of the printer, the Delta printer we had, with the help, of course, of Florian and Stefan from Delta Tower and Hypecask, we were very, constrained by number one, the fact that it was in China, number two, the size of the printer, number three, the budget, of course. And so what happened? We have this new software we can use to generate our own plugin, our own G-code. We have these machines that we posted to China instead of posting the actual product. And so it's completely upside down, because the client, instead of receiving an installation, receives machines. And then he has to run the machines directly from China. And so we have to tell him what this means. So this is Grasshopper. This is how every file would look at the end. We had 200 of these files. Each file is approximately the size of, I think, 10 times the Bible. And so we send them to China. And then they have to actually print them continuously, whilst letting us know, how we're doing. So this is the shape, and this is what we did. So eventually it ended up being like parametric 3D printing, in that we would vary the speed of the extrusion, and we create effects based on the fact that we could change the properties of the print as we print, which is something you cannot do with conventional software. So we could write names. This is an image of my phone at the time, constantly checking the prints as they were printed. And it was just really an exciting experience, because people could actually go and see the end result as well as the process. So we printed as we went, right? And coming back to London, an art gallery commissioned us to do a kind of light-specific installation. And this is the Silkworm in action. And you can see these little wires being printed. They're still in the same spirit of the fabric we used for Karen Millen, but in this case we made our own sponginess, right? You remember that material I showed? And we generated that G-code in order to shape the toolpath, which would then capture the light and would be held by the shell around it. So this is an image of it. So you have the shell around it. The light would be inside the tube here, and would be captured inside these strings, which really gave an impression of diffused and almost magical light, which had a great quality. So this is a quick simulation we did to show how light would behave inside. So instead of doing a sun simulation where it's from outside to inside, it was from inside to outside. And what we noticed is that each one of those bulbs here would capture the light and would diffuse it back inside, and inside it would get scattered. So from a kind of a very cheap project that we did for Carolyn that had its own values, we actually informed then the machine, made the machine cheaper and more affordable in order to build large-scale projects, which we then used to do pop-up experience, in which, in this case, people would put their head through and see how light can be diffused in different ways. Now, this is the skin of it, and had all these interesting effects that added to the value of it. And this is when my friend and client, Anthony, came and said, I want to do a 3D printed restaurant. And of course, he loved the lamps, and he said, but can we sit on them? Can we use them to design a whole range of furnitures? So this is the first kind of set of drawings we created. And also in parallel, what I did is I went to a workshop in Taiwan to actually push Silkworm to see how fast it could print. And we ended up with results that were printing, that height in half an hour compared to people that printed the same height in like 15 hours. So coming back from that, what I did is I applied the concept of truss, which is very common in engineering. And we used that, and we kind of extruded a soft truss. Soft in that it curves around, but of course hard because it still shapes a truss. And by adding waviness to it, what you ended up is with a very, very strong truss in 3D, which is something that we can actually sit on. Now, I know this seems like a weird picture, but I make it a point that you can actually sit on it, and to the point that the whole restaurant will have them. Now, the process behind it is, of course, intensely computational in that we actually generated a matrix of potential chairs, and we added the constraints within the computer. So what happened is we checked the speed of the prints, the angles behind the print, and then generated a whole range of families that would respect these constraints. Because of height constraints, what happened is we created male-female connections, which is what I have here. And you could go as high as you wanted, which means that together with the laser that creates the horizontal surfaces, we can create a whole range of furnitures with the 3D printed constraints. So this is happening next month, and I hope it'll still work. But yeah. So moving on to probably the last project then. This is the wooden wave at Burrow Apple Engineering. So what happens when you understand digital fabrication is that it's not just 3D printing, that if you want to do wood, a lot of people are like, can I print with wood? And I said, well, you might as well cut the wood instead of trying to print the wood. So the difference between additive versus subtractive manufacturing. These are things that I try to explain at every 3D printing conference so that people understand that it's a wider revolution that is happening, that is not just the 3D printing aspect. So this is the space that Burrow Apple gave me after giving a talk like this one, saying we want a piece that would kind of activate the space, play with the ceiling, and create a more intimate experience. And I remember the client going, oh, why don't you just kind of go around all the obstacles around you? So the space was very linear, and what happened is they really liked the Karen Millen project, the very first one I showed. But of course they wanted it for 5 years. So to make a piece permanent, we had to use a material like wood. But how do you make wood bend in 2 axes? It's almost impossible geometrically. And that's when I discovered this guy, Aaron Potterfield, a brilliant person and maker that created that set of what's called parametric curve. And what happened is you use that and you can fold any piece of wood thanks to those springs. So those springs create flexibility, and you can start bending wood in all kinds of directions. So again, thanks to parametric design, what we did is a variation of possibilities and check the patterns that would fit our initial concept the best, informing the concept itself. So based on the size of our laser cutter, and adding those supports behind, supports that are also generated through structural analysis called topological optimization, we ended up with this, which is the 2D file, which ended up folding into things like this. So a flat pack, really cheap, very simple process, but that ended up with real magical effect where people were, how on earth is this happening? But it's happening through the understanding of wood and through the kind of improvement of an open source concept. Now this went back open source, of course, and is downloadable on the Instructables. Now, being engineers as clients, they wanted these panels to act in many, many different ways. Light diffusers, sound absorbers, temperature diffusers. So when we started placing them, so this is an image of us printing the entire plan and then starting to locate each of those pieces. We did two pieces. We did one in their main headquarters, 17 Newman Street, and then the other one being a bit lower, they wanted it to be more open. So we started opening the pattern and noticed that the fractal nature of this pattern made it much more natural than, say, an imposed rectangular pattern, which is a good lesson for any designers to seek for the fractal ornaments. This is the phase-changing material, which it melts when it's hot and then releases heat when it cools down. So as for every project, we installed it ourselves and created this kind of modularity so that we didn't have to create many, many files. All we had was 3 modules, and we could create that kind of ceiling. Now, I really feel that the rise of making in architecture allows you to have a direct contact with your design as an architect, meaning that you're back to an empirical process similar to the master builders of the cathedrals. And what happened is they would try, they would fail, they would try, they would fail. And thanks to that, I think there was a sophistication happening in the cathedrals that was lost as soon as you separated the designers from the makers. And so I really feel that this could come back and that we could have much more democratic cathedrals. Now, these cathedrals, we try to bring them into a festival called Burning Man with our students. That's when we give our students the opportunity to learn the 10 principles behind Burning Man, which are, world famous now: radical inclusion, gifting, decommodification, amongst others. They bring a kind of a spirit that companies like Google or Facebook are trying to implement in their companies. Now, why are they cool? Why are they adding to the knowledge of our students? Well, we want them to understand simplicity and complexity, and we want them to understand that a simple module assembled in a clever way could create really incredible, sophisticated results. But for that, we need to establish that loop between the physical object and the digital object. Now, these are models that our students create. I'm giving one example of a project that wasn't built, but from a very simple spike to that type of assembly was really just, a similar logic, but a different arrangement. So when we started going to Burning Man with our students every year, this is where we started. We started with a kind of narrative that was directly influenced by the materials they would choose. So in this case, wood. They would create curves, or in this case, the coach pattern, which is what you call a recursive pattern, in that you take the first object, it repeats on itself, and so on and so forth. But he made it out of scaffolding. So there's always this little constraint, or little big constraints of cost and assembly in a very hot environment. So they make a lot of models. This is our friends from Format Engineering who help us a lot. And this is the type of machines we deal with there. So of course, much bigger laser cutters, which allow us to send our files and assemble them like giant IKEA kit in the desert. Now, it never works as planned. You forget elements most of the time. But this is really an architectural bootcamp, a kind of making community on an architectural scale. So this is us during storms. This is our camp with all the students. This is trying to assemble a scaffolding into a recursive shape. So really, geometry defines what can be done. Also the materials, also the environment. The fact that we have to leave no trace whatsoever after we leave, and that we arrive with a whole truck full of stuff, and that nothing else can be added later on. So this was the very first experience, which created really interesting effects. nighttime being as important as daytime. And these were the second set of projects that we created. The last project that you just saw, this, very cool as a render, very interesting, but took everything out of us. It was a giant recursive tree made from a very complex script called Reatomic Surface. And what happened is the engineer, from the render to the realization, told us your forces are way too high in there. So when we ended up with too many pieces that entered each other through a kind of recursive way, because if you moved one, all of them would move. So there was a real problem there. And I think we faced the limit of what you can push when you push digital technology applied to a pavilion. We ended up with so many pieces that were not named. And so we had to name them, we had to find them, we had to assemble them. And on top of that, because it wasn't form found and that it wasn't structurally stable, we had to add those massive metal columns, which we had to assemble. Now, this is Aaron Potterfield. Remember him? Well, he became our friend, and now he comes with us to Burning Man. And he's the one that posts back all of this into the open source platform Instructables. So this is, we couldn't even finish it. And it was a really difficult project. This was, on the other hand, a very simple and really beautiful alternative on which we learned a lot, because they were just simple off-the-shelf timber that were offset from one another with structural screws. So whilst we were struggling on our side, the other group of students were assembling these panels together, like a charm, and it worked really well, and it burned perfectly. So these are a couple images of the final project, including that one, which worked really well as well. And this is where we're taking it, having learned from failures and success. This is the new baby, and this is what we're building this summer. The Kickstarter will go online soon, so you can help us build it. This is a little video that summarizes it. It's basically a kind of set of tangents that rotate around a sine curve. So with a central column and horizontal members that hold what we call the tangent, on which people will write words, and we will be able to climb it and look at the whole desert through those words. So quick animation that shows it, that shows the magic behind it. So these woods will sway in the wind, and just hope that it will create a really beautiful effect together with the LED lights. So thanks to Parametric design, again, we could iterate and see what sort of material we can use. And having learned from the previous project, using off-the-shelf material is absolutely crucial. Instead of always wanting to push digital technology, digital technology can inform off-the-shelf materials. It doesn't have to always be digital fabrication with digital design. And that's something I've learned with time. You see the night view using fiber optic cables and the day view, based on these simple pieces that are assembled together into that. So these are different tests of the tangent and how they will end up. So just showing you how it went from highly technologic to very low tech in a way, uniting high technology with a kind of making loop and understanding of constraints is what informs all these projects. So that's my conclusion. And yes, so hoping to work with some of you out there. Contact me and be happy to take you in our journey. Thank you very much.
So, thank you very, very much, ladies and gentlemen. That was the last presentation from today. I'd like to thank Arthur from all of us. That was one of the most interesting presentations. Fantastic introduction into parametric design and architecture. And I would like to thank Arthur one last time from all of us for this fantastic presentation. Thank you very, very much.
Thank you very much, Jan.
What the fuck is going on? I would like to introduce you to Arthur Mamou-Mani, and he's... Let's do that again. So, welcome ladies and gentlemen. I would like to introduce... Shit.
You're screwing me up now. So, hold on.
I would like to introduce to you a very special guest this evening. Arthur Mamou-Mani from London. He's going to explain...
Mamou-Mani. Mamou-Mani. Money.
Can we take put a picture of him here and I'll just do Arthur Mani from London.
Are you shitting us, man?
Arthur Mani.
No way.
I didn't do anything.
I looked at the really professional. My good old friend for the face mask.
He's gone.